Okay, recording has started. Okay, so welcome everybody. Good morning and welcome to second lecture for this class. Let's see, what we're going to do today is kind of finish up what we were talking about yesterday when we were talking about, hang on, that's probably somebody who can't get into the Teams. No, there we go. Okay, so we're going to finish up what we were talking about yesterday with these interval notations. Then we're going to talk a little bit about unions and intersections, absolute value, integer exponents, and then we'll move on to do some work with polynomials. We'll practice adding and subtracting polynomials, so combining like terms. You may have done that before. And we'll practice factoring polynomials as well. Okay, so let me get the screen shared on the iPad. Screen. All right, and really fast before we start, let me ask, are there any questions about the syllabus or administrative questions or what we covered last time? Okay, then we'll start. So let me remind you, last time we were talking about how to convert between interval notation and this kind of less than or equal to signs and less than signs. And the main thing that we learned was that if we have a less than sign, but not a less than or equal to sign, that's going to correspond to a parentheses, okay, a curvy parentheses. And if we have a less than or equal to sign, that's going to correspond to a bracket. Okay, so for example, the way we translated 2 less than x less than 10 to interval notation was we said then that x lies in the interval 2 comma 10, where we used these parentheses on the sides here. And then we tried a couple more. We tried one that was half open. Okay, so it's okay for one side to be a bracket and one side to be a parentheses. That is possible as well. And we also tried this funky example down at the bottom where the information was packaged a little bit differently. So we got 2 pieces of information. We got x greater than or equal to -3 and x less than or equal to 0. Let's see, there's a question in here about my math lab. I just talked to the Pearson rep yesterday. They finally got back to me. So I'm still setting up that portion of the class. So hold off on buying math lab for the time being, okay? All right. So yeah, we can sometimes get our information packaged a little bit differently. We just sometimes have to clean it up a little bit. So that's what happened between this first line and this second line here. We just rewrote it a little bit differently, and that made it easier to see how we were going to write it in interval notation. So we said that x lies in -3 comma 0, and we used brackets because we want to include the endpoints. Okay, so that's a brief recap of what we did last time. And now we're going to talk about unions and intersections, okay? So unions and intersections are operations which we can perform on multiple sets, okay? So if we have a Venn diagram here, we can have these sets A. Am I meaning to share my screen? Yes, I am. Can everyone else see my screen? Okay. So then that might be a problem on your end. You might try rejoining the meeting. That might work, or it's possible that you need to, let's see. I'm not sure if you can click on like things on the bottom to bring them up. Not sure about that. Okay, so my recommendation is to try rejoining the teams, and if that doesn't work, then you may have to just watch the recording for today, because I know that the recording is getting my screen, so we can work that out. Yeah, we can work that out another time and see what's going on with that. Sorry about that. Okay. So carrying on, so if we have two sets A and B, we have these operations unions and intersections. And let's describe first what a union is. A union is a union of two sets is a new set which contains everything in either A or B. Okay, so A and B are our sets here, so we would say that the union of the two sets A and B is all of the elements which are contained in one of these two circles or both. Okay, one of these two circles or both. So in our case, that's going to represent the shaded region, which is shaded in orange. Okay, so A union B, that's how we write it. Okay, A union B. Okay, so what we mean when we say A union B is we're referring to a new set, which is, if we were to sort of draw this set to the side, it would look something like this. Okay, that's A union B. Okay, and we have another set operation, intersection, and the symbol which goes with intersection is this kind of upside down union sign. It looks like an N, sort of, so I like to put it in the intersection because that's how I remember them. And let's write down the definition. An intersection of two sets A and B is a new set which contains everything which is in both A and let me write that in green, and B. Whereas previously we had A or B. Okay, so those are the sort of crucial words that go with union, intersection. Union goes with the word or, and intersection goes with the word and. So I'm being sort of more specific if I ask for an intersection. I need my items to be in both sets. Both A and B. So in our picture, A intersect B is going to be represented by this pink region of items which are in both of the circles. Okay, so that is the definition of a union of two sets and the definition of an intersection of two sets. Does anybody have any questions about unions and intersections? We'll do some practice in a minute here. Okay, well, if you do think of any questions, just go ahead and either use the raise hand button, hopefully I'll see you, or you can type your question out in the chat, or you can just unmute yourself and interrupt me at any time. Okay, so we just talked about intervals, and now we're talking about unions and intersections of sets. So let's try doing some unions and intersections of intervals. Okay, so we're going to do these practice problems here. So first of all, let's recognize here that intervals like -3, 4 and intervals like 2, 6 are indeed sets, right? They are sets of numbers. It is a set which contains every number which is between -3 and 4, excluding the numbers -3 and 4. Okay, so these are sets, and we can take their intersection. And so what we want to do is, if we want to... Oh, sorry, I'm getting some reverb on someone's microphone. If you could mute yourself, that would be great. Thank you. Okay, so if we want to take unions and intersections, we just have to think of the elements which are in both sets or either set. Okay, so let's try doing, we'll stick with the notation from before. We'll use orange for union. So in this first one, we should have A union B is going to be equal to -3, 4 union 2, 6. Okay, so we want to consider a new set, which we want to write a single interval here. Okay, so in my blank, I want to write a single interval which expresses the interval which we would get if we said we want to make a new interval which combines both of these into one. Okay, so a new interval which expresses all of the elements which are in either of these two sets. So let me pose that question to you all, and you can type it probably into the chat if you have an idea of what we should use. And while you guys think about that, I'll write out the notation for the next one. Okay. Looks like Leah's got an idea for A union B. And it is the set. Looks like 2, 4. With a bracket on one side and a parentheses on the other side. Let me write that in black. All right. So Leah was brave and went out on a limb here. What do we think? Do we agree with Leah? Okay, another answer coming in, -3, 6. That's another possible answer. I think both of these are good for each of these answers here, but we got to figure out which one should go where. What do we think for A union B? So let's talk about this highlighted box here. Okay, we want to do A union B. We want to consider the set of elements which is formed by taking the set of elements which are in either A or B. So let's have a show of hands if we think we should use 2, 4, and then we'll do a show of hands afterwards if we want to say 3, 6. So let's see a show of hands for the green answer for A union B. Okay, how about for the second answer? -3, 6. Show of hands. You can raise your hand in the... Okay. All right, a few more answers for that one. Okay, that's good. That is the one. So we should use this second answer for the first blank. So let me erase and get that in there. And then I'll illustrate what's going on with a number line. We should use this answer. Okay, so here's what's going on the number line. We've got -3, 2, 4, and 6 here. And our first interval is the interval -3, 4. So let's draw that in. We would draw it in with parentheses, like this, -3, 4. Okay, and the first interval is everything that is in between those 2 points, excluding -3 and 4. If you did some graphing in your algebra classes, you might have put like a hole on the number line to represent that the endpoint is not included. Okay, and then for the second interval, let me use a different color. We'll use pink. For the second interval, we've got 2, 6, but the endpoints are included. So I would put a dot here, filled in dot, and then I'd draw, and then I'd put a filled in dot here. Okay, so if I want to consider A union B, I should consider the set of things which are in either of these two sets or in both. So I want to consider this entire interval, and I have an open endpoint on the left and a closed endpoint on the right, which is why we should have on our answer the parentheses on the left and the bracket on the right. Okay. You could also illustrate this even a little bit further. You could consider these as like, sort of as being like our circles from before. You can think of the first circle being here. That's A. And the second circle being like this, and that's B. And remember, A union B was all of this stuff. Okay. All right. So hopefully that's starting to make more sense now. So where should we put the other answer? Is the other answer good for our intersection? What do we think? Yes. Okay, sweet. All right, yeah, we should put the other one in for our intersection, and I'll draw the number line once more so that we can see. Got -3, 2, 4, 6. Our first interval went from 3 to 4. And our second interval went from 2 to 6. So if we want to consider the set of elements which is in both sets is going to be this right here, where we see green and red overlapping one another. Okay, green and red overlapping one another. And I will pay specific attention to the fact that we included this bracket on this left-hand side of this interval. The reason we included the number 2 is because the number 2 is included on the red by virtue of having a closed dot, and the number 2 is included in the green section by virtue of being in the middle of the interval. Okay, so we do want a bracket on that side. And then on the other endpoint, our 4 here, we use a parentheses. The reason being that although 4 is included in the middle of the red interval, it exists as an open endpoint for our green interval, which is why we're not going to include it. Okay, so in this case, we have 2, 4. Okay, wonderful. Okay, so again, I'll pause and ask. There was a bit of a jump from defining unions and intersections to actually computing them with intervals. So I want to make sure I haven't lost anybody. Are there any questions about how we started doing this process before we see some more examples? All right, we feel okay? All right, I see one hand raised still. I think that's Heidi Duncan. Is that because you have a question or you just forgot? Seems like maybe you just forgot. Okay. All right. Before we move on to the next, yeah, no worries, no worries. Before we move on to the next problem there, I want to include one more thing which I almost forgot to talk about, which I meant to get to last time, but we didn't have quite enough time. And that is how to deal with intervals which don't necessarily have a right or a left endpoint. Okay, so let's try one more of these interval problems. So we're going to switch gears for a second back to this less than or equal to notation and our interval notation. And let me ask how we might write the interval for the following problem. If we just had x is greater than or equal to the number 1, then we wanted to say x lies in the interval. In our case, we have a lower bound of +1 and no upper bound. Okay, we have no upper bound. And so the way that we are going to treat this is by saying, yes, we have our lower bound and it should be a bracket because we have a greater than or equal to sign. We should put 1 in here. Then what should go on the right-hand side of this interval? Let me ask the class. What do we think? Has anybody seen this before? That's right, Leah. We should put infinity on the right-hand side of the interval. And let's see, Leah, we'll see if you can go for gold. What do you think we should have, a bracket or a parentheses? Parentheses, that's right. We should use a parentheses here, okay? And the reason why we always use a parentheses with infinity is because infinity is not actually a number, right? What we're saying here is we have if we have our number line, we have the number 1 here, and we're saying that our bracket is just going like this on and on forever. If we were to put a bracket here, it's kind of like saying that eventually there's a point where, okay, that right there, that's the point infinity. But then there's always some point beyond that point, which would then be something like infinity plus 1. And we know that infinity plus 1 is equal to infinity, so we don't actually use a bracket because that would imply that infinity is, in fact, a finite number, which is sort of absurd to say infinity is finite. It's like an oxymoron or something. No, it's worse than an oxymoron. It's a paradox. So we use parentheses when we talk about infinity. Okay. So maybe I'll make a note here. Infinity plus or minus infinity always goes with parentheses. Okay. So likewise, we might have something like x is less than 5. We might rewrite this as x lies in the interval negative infinity, comma, 5. And we would use a parentheses on the right-hand side. So in this case, our number line looks like here's 5, and we go to the left, on and on forever. Okay. By the way, thank you all so much. We got like so many people answering my questions in the chat. I think I have more participation in this online class than I did in my in-person class last semester. So thank you all for taking the time to type that stuff out for me. Okay, that's great. So any questions about intervals at infinity? Okay, then we will move on and do these next 2 examples. Maybe I'll... Oop. Yeah, there we go. We can have some space here. So let's try this one. Okay. So let's try A union B first. That's going to be equal to negative infinity, comma 5. Nice. Shrudi's already got the answer. I'm ready to roll. I like the enthusiasm. Thank you. Union 2, comma infinity. So we just want to take all of the things which are in either of these 2 sets, and if we were to draw it on the number line, we'd have 5 and 2. And on one interval, we'd have red going to the right, on and on forever. And on the other one, we'd have green with a parentheses at the 5. But it doesn't matter because it has overlap. And this is what these would look like. And if we took all of the elements which is in either of these 2 solid green or solid red parts, then we would get the entire real line. And the way we would write that is exactly how Shruti put it in the chat. It's going to be negative infinity, comma, infinity. I should have gone back to orange. And we'll use parentheses. All right, and then we'll do A intersect B. That's going to be negative infinity, comma 5. Intersect 2, comma infinity. Oops. Should be a parentheses. And what are we thinking for this one? Okay, looks like Leah's got it. Shruti was nearly there, although we want to point out that we should make sure to preserve the fact that this is an open Oh, that's a really bad highlighting color. The fact that this is an open circle for the green interval means that we're going to need to exclude 5. Since it's not in the green interval, it can't be in both the green and the red interval. Okay. So our interval here is going to be 2, 5. But we're going to keep a bracket on the 2 since it's in both, and we're going to keep a parentheses on 5 since it is not included in our first interval here. Okay, any questions about that one? Hopefully this is starting to become clear. Okay, I'm going to leave this last one as an example for you guys. You guys can try it at home if you want, but we're going to move on and talk about some other things. Okay. So next up, let's talk about the absolute value. This is just a really quick note, really, on the absolute value. It's not going to be, we're not really going to talk about this in depth right now, but we will later. But I just want you guys to recall briefly what the absolute value means. So if we have an absolute value sign and we put in a positive number, the absolute value sign does absolutely nothing at all. However, if we take an absolute value sign and we put a negative number inside, it'll turn that negative number into a positive number. So the function of the absolute value is to take the number that's inside of our poles here and make it positive. Okay? So you can also define absolute value as being a distance. So we can take x minus y to be the distance between x and y. So let's see if I can draw that. So we've got 0 here and x and y. Then if we want to know what this distance is, well, if we take x minus y will be a negative number since x is smaller than y. So x minus y is less than 0. It's a negative number. Since x is a smaller number than y, we subtract something bigger, then it's going to be a negative number. Is going to be equal to, well, we should negate whatever's inside. So it should then become y minus x. And that's going to give us exactly this distance here as a positive number. Okay, so that's one way to interpret what absolute value is doing. And you can also think of it as being sort of the absolute value of any number is just the distance between that number and 0. So we'll use the same example that we did above with 5 and negative 3. If we have 0 here, 5 here, and negative 3 here. Remember, we always express distance as a positive number because there's no way to walk negative 3 miles. We say we walk 3 miles in the other direction, right? So this distance here is a distance of 3, and this distance here is a distance of 5, and those are both equal to the respective absolute values of those numbers. Okay, so that's a brief recap of what the absolute value is. Are there any questions on absolute value? No questions from Shruti. Okay, well, if you think of any, don't hesitate to either raise your hand or turn on your mic or talk in the chat. I don't mind going back if you think of something later. Okay, so finally, the last thing that's in this particular part of the lecture, this is sort of section 1. We're going to get to some section 2 today because I think today's class goes until 9:45. But we're going to start by talking about some exponents here. Let me get my notes up in front of me. Okay, and the way I'm going to define exponents is going to be in a sort of bit more of an abstract way than you might be used to saying. So let's start by saying assume that A is an integer. Okay, so A is a value, an integer value. So something like A is going to be equal to something like 1, 2, 3, -9. Whole numbers, but possibly negative. Okay, that's what an integer is. Whole numbers, but possibly negative and possibly 0. Okay, then we define x to the power a. So for example, x to the power 2 or x to the power 3 in the following way. Let me hedge my bets first by saying if a is larger than 0, then we would say that x to the a is equal to x times x times x times dot 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 times x, and we multiply x times itself a times, where a, remember, is an integer, and we said that it's larger than 0 for the time being. So if a were to be 3, for example, x cubed is equal to x times x times x. Okay, so I think that this notion should be fairly familiar about x cubed. You may not have seen the sort of more general form of x to the a being written out this way. That's just sort of a more mathematical way of writing the definition of this because it's more general. I don't have to rely on a specific example. It sort of, you know what to do for any a, which is an integer larger than 0, and so on and so forth. Okay, so that's how we define integer powers. We do note that x to the 0 is equal to 1. And I will write except 0 to the 0 is undefined. Okay, and what that means is we just say 0 to the 0, that's just way too confusing for us. We're not going to deal with it. Okay, so 0 to the 0 is undefined. We don't know what it is. Okay, but if x is just some number like, for example, 2, 2 to the 0 is equal to 9 to the 0 is equal to pi to the power 0 is equal to -3 to the power 0 is all equal to 1. Okay, so no matter what number we take, you take it to the power 0, we get 1. Okay. So now I'll try to involve the class a little bit here. See if you guys can remember from when you probably learned this for the first time in maybe algebra. Let's try. All right, try. All right, try. So try on your own. Let's see, what do we think we should do with something like this? We multiply x to the a times x to the b. Let's see what we're going to get there. Okay, so I'll ask you guys, what do we think should go in this blank here? Okay. Very good. Three answers, which I think are saying the same thing. Add the exponents. We do x to the a plus b. Okay, very good. This becomes x to the a plus b, and let's see why. Let's do the example of x squared times x cubed. Well, by our previous definition, we said that x cubed is going to be x times x times x. We know that x squared is just going to be x times x. So this is going to be equal to x times x, that's x squared, and we're going to multiply that times x times x times x. And we've got a total of 5 x's here. So we write x to the 5th, and that is indeed 2 plus 3. Okay, so that's an example of why that works. And the other one that I better add a page here. The other one that people often get confused with this rule is this one. When we do x to the power a to the power b, we want to find out how we should write that one. What should we do in this case? Yep, Heidi's got it. We should multiply. Okay, so we should multiply the powers in this case. We should do x to the a times b. Okay, and again, we can use the same example. We'll do x 2 and 3. How about that? X squared cubed. Well, by our definition, if we take something and cube it, that means we should take that thing times itself 3 times. So that would be equal to x squared times x squared times x squared. And by our previous rule, we know that if we multiply two things with powers, we should add those powers. So we'll get this is equal to x to the 4th times x squared. And then we would simplify that one by adding those powers, and we would get x to the 6th. And since 6 is equal to 2 times 3, you can kind of see where we're going with this. Okay. So this can be proven in a little bit more generality, but this is a kind of a good way of visualizing it as an example. Okay, so that's integer exponents. Let's see, we should probably talk about negative exponents. So let's see. Let me not use orange. It's kind of hard to see. If we write x to the negative a, where, again, a is some integer larger than 0, then we define this to be 1 divided by x to the power a. Okay, 1 divided by x to the power a. Okay, and if you want to see a reason why, we can kind of look at the following. If we consider 1 here being in the center, and if we decide that each time we go up the ladder, we multiply by x, we'd get then x, and then x squared, and then x cubed, and then x to the 4th. And as we see, if I were to go down the ladder, what's happening is I'm dividing by x. Okay, so if I go up, I'm multiplying by x. If I go down, I'm dividing by x, dividing by x. So by this logic, we'd have x to the negative 1 and x to the negative 2. And if we're dividing 1 by x, then that means that x to the negative 1 should be 1 over x. X to the negative 2 should be 1 over x times 1 over x, because dividing by x is the same as multiplying by the reciprocal, equals 1 over x squared. Okay, so this is just to say that this definition makes sense. Okay, so if we take a negative power, we put the thing to the denominator and we make the power positive. Okay, that's all we do. Okay, so Yeah, by that logic, let's try simplifying x to the a divided by x to the b. Okay, what should we do with the powers in this case if we have x to the a divided by x to the b? Subtract. Okay, great. Yeah, we should subtract. I'm going to come back to your question in 1 second, Devin. Okay, I'm seeing lots of subtract, and that's correct. We should take, well, we can rewrite this. Dividing by x to the b is the same as multiplying by the reciprocal 1 over x to the b. And we just decided that 1 over x to the b can be written as x to the a times x to the negative b. And we have a rule for x to the a times x to some other power. We would take those powers and add them. So that would be x to the power a plus the number negative b, which adding a negative is the same as doing subtraction. Okay, so that's how we would write that. So Devin asked a great question. Can the numerator be a number other than 1 for x to the minus a? And I'll first assume that you're just talking about x to the power a. It's always going to be negative a is always going to be a numerator of 1 in this case. However, if we had something like 3x to the negative 4, in this case, we only know how to translate this part of the equation. So the way we would write this is we would keep the 3, and then we would rewrite x to the negative 4 as being on the other side of this multiply sign as 1 over x to the 4th. And in this case, we would get 3 divided by x to the 4th. So Devin kind of brought up a really important point, which is that if we have things being multiplied, okay, the power here, this negative 4 power, only applies to the x. Okay, it only applies to the x. So in other words, only the x goes down to the denominator, and we would keep the 3 on top. Does that sort of answer what you were asking, Devin? Yeah, okay. So yeah, if we just have x by itself to some negative power, we just move it to the denominator and the numerator will be 1. Okay, it comes from this ladder type of thing here. Remember, 1's right in the middle, so if we go down 1, we should take 1 and divide it by x. If we go up 1, we should take 1 and multiply by x. That's where it comes from. Thank you for asking that question, because that I had almost forgotten about remembering this. There's one other case in which the 3x, the 3x to the negative 4, the 3 would travel to the bottom. And that's if we had parentheses around the entire thing. In this case, the negative 4 power does apply to both the 3 and the x, and this would be equal to 1 over 3x to the power 4. Okay. Remember, we've got Pemdas, so parentheses come first, and then Mdas after, so E being exponents come after parentheses. So we preserve the parentheses first, and then do exponents. Okay, so that's the only case in which case the power would apply to both terms in the multiplication. Okay. Let me add yet another page. and talk really briefly about distributing. And I'll just state these two rules. If we have parentheses, x times y times z to the power a, if we have these things being multiplied in the parentheses, then we should distribute the power a onto x, y, and z. However, I will give you guys a warning that we can only do this if we're multiplying these things on the inside of the parentheses. For example, let me write a note. I'll write a note. If we do x plus y plus z to the a, this is not going to be equal to x to the a plus y to the a plus z to the a. And I'll show you why. The example I'll use is x plus 3 squared. Why should this not be equal to x squared plus 3 squared? What should it be equal to instead? There's something I forgot to do. That's right. Catherine's got it. We should FOIL. If we have a binomial expression and we square it, that looks like this. If we were to expand it out, remember, if we square something, it just means multiply it by itself. If I put it like this, I bet you guys would remember that we definitely have to FOIL here. We would get x squared plus 3x plus 3x plus 9. So that would be x squared plus 6x plus 9. Okay, so be careful if we have addition or subtraction in the parentheses in a power, we can't just distribute the power. We can only do it if we're multiplying or if we're dividing. That was its own kind of sidetrack. The other thing we have is that if we have x over y to the power a, this will be equal to x to the a divided by y to the a. Okay. All right. So any questions about all of these integer exponent rules that we've covered so far? Okay, sounds like not. If you think of anything, feel free to ask. Otherwise, I also have office hours after class tomorrow, so if you don't feel like asking during class, you can ask then. Okay, so let's try some examples. We want to simplify some of these things. Let's try this first one first. We got to do 3 divided by 5. Well, I just told you guys that if we have this 3 divided by 5 and we have a power out front, we're going to distribute that onto the inside. We can write this as 3 over 5, where we put -2 power on each of them. And to truly simplify an expression like this, we want to have an equation with no negative exponents. So the way I'm going to rewrite this is I'm going to kind of write this as, well, I want to write it in a way that our rules can apply. I know a lot of people probably know exactly what to do at this point, but I want to just be really careful here. So I'll write it as 3 to the -2 times 1 divided by 5 to the -2. And I'll rewrite the first one as 1 over 3 to the second power, and I'll rewrite the second thing as 1 divided by, well, 5 to the negative 2 would be 1 over 5 squared. And keep the same thing on this one, and we'll rewrite divide by a fraction, we'll multiply by the reciprocal instead. So we'll do 1 times 5 squared. And if we were to simplify that, we'd get 1 over 3 squared times 5 squared, which is going to be equal to 5 squared over 3 squared. Okay, I know that was a little bit tedious, and you might find it strange for me to write it this way, but I'm writing it that way just so that we are relying only on the principles which we've already shown above. Okay. The shorthand, I think there's probably a lot of students who could just go straight from the start all the way to here. They just know, okay, if we have a negative power, we just move it to the bottom and make the power positive. Likewise, if we have a negative power in the denominator, we move it to the top and make the power positive. But here's a kind of a description of why that's happening. Okay, great. So that's one. We'll do the next one as well. So if we want to do 4x squared times y cubed times 7x cubed times y, well, we're just going to write it out. Again, I think a lot of people will know exactly what to do here, but let's be extra careful. We'll write this as 4 times x times y times y times y. And we'll multiply that times 7 times x times x times x times y. And the rule that I'm going to use here is called not distributivity. It's called abelian. What is abelian? Commutativity. That's what we call it. Okay, so we're going to use the commutative rule for multiplication, which says that, for example, 2 times 3 is the same as 3 times 2. We can do multiplication in any order. And the order that I'm going to do this multiplication in is I'm going to group up 4 and 7, and I'm going to group up all the x's. And I'm going to group up all the y's. And that's going to be equal to 28 times x to the 5th times y to the 4th. Okay, and again, I think there's a lot of students who would go straight from here to our answer, but this is just the real reason that we could do this. So from here to here, this was by commutativity of multiplication. Okay, so the long short of it is that what we can do is just kind of take all of the powers on x and add them up, and then take all the powers of y and add them up, and 2 plus 3 is 5, so we got a 5 here for our power on x, and then 3 plus 1 is going to be 4, so we get y to the power 4, and then we multiply the terms 4 and 7 as well, because those are our constant terms, and that's how we got 28. Okay. All right. Any questions on those first two? Okay, again, I don't mean to torture you by going through this stuff. I just want everyone to see why it works the way that it does. So if you can go straight to the end, then great, but make sure that you're doing it correctly and you know why you're doing it. Okay, let's try this next one. Copy that, we'll put it down here. It's getting a little bit crowded up there. Okay, let's try this one. On this one, we want to first use our rule to distribute this -3 power, right, onto each of those two pieces. So first of all, first thing we'll do is distribute the power. So it'll be 5 times -3. Why don't we actually take even one further step back? We'll distribute the power. We'll get x to the 5th to the power -3. And we'll divide that by 2y to the -3, and we should keep this in parentheses, and we'll take that whole thing to the -3 power as well. Okay, now let's handle the numerator. We have a power to a power. We should multiply those powers. We should take 5 and -3 and multiply. We get x to the -15. And on the bottom, what should we do with this -3 power here? Is it going to apply to just y to the -3, or should we also make something happen with this 2 here? What do we think? Asking the class, what should we do with this -3 power and this term here? Yeah, we should apply it to the 2 as well. Thank you, Chris. You're exactly right. So because we have these parentheses here, and we have things being multiplied inside, remember we had a rule, if we multiply things inside of the parentheses and we apply a power, we have to distribute that power. So I'm going to distribute it. I'm going to write 2 to the -3 power, and then I'm going to multiply that by y to the -3 to the -3 power. And I'll clean that up a little bit more. We'll leave x to the -15. In fact, we'll even leave 2 to the -3, and we'll just clean up that part. We have a power to a power on our y. We should multiply. We'll have y to the -3 times -3. So -3 times -3, negative number times a negative number gives us a positive number. So we'll have +9 there. Okay? And now the last thing that we should do is to make all of our negative powers positive powers by moving them up or down as needed. So the -3 power of 2 should come up to the top. It should be 2 to the 3. And then we should divide by x to the 15 and times y to the power 9. And we leave y on the bottom because it already has a positive power. Okay, so that is how we would handle something like this. That's how we would handle something like this. So we just really need to remember the principles of Pemdas, okay? Whoops, there's no B in Pemdas, is there? There's a D. Pemdas, so parentheses first, then exponents, multiplication and division go together, addition and subtraction go together. Okay. Yeah, Morgan had the same idea. Apply it to everything. Good. Okay, let's see. Is this last one worth doing? No, but I will make one note. Okay, what should the note say? The note says -x to the power a is going to be equal to just x to the power a if a is an even number. And -x to the a, why don't I write it with proper notation? Oh, that's not a very good one. There we go, that's better. -x to the a if a is an odd number. Okay? So the reason being, if we take -x squared, it'll be equal to negative x times negative x. Negative number times a negative number is a positive number. And if we were to take negative x and cube it, we would get negative x times negative x times negative x. And that would be negative x cubed because we have 3 negative signs. We have the first 2 multiplied, we'd get a positive, and then we would take a positive times a negative and get a negative again. Okay, so that's one thing that I do want to note down here. Okay, now let me check my handy notes here and make sure I covered all of the common mistakes. Okay, I think I covered everything that I wanted to cover from this section. So in our last few minutes here, transition and talk a little bit about polynomials. Okay. All right, so let's talk about what a polynomial is. It's essentially it's a sum of powers of x with non-negative integer powers. Okay, so what does that mean? Non-negative integer powers. Hello? Somebody have a question? Someone's mic accidentally turned on or something. All right. Let's see here. Non-negative integer powers, what does that mean? That means numbers like 0, 1, 2, 3, ... Okay. So non-negative integer powers. So for example, a polynomial could be something like x squared or x cubed minus 7x squared plus 2x plus 1. Where here the 0 power was being on 1, you can kind of think of there being an implicit times x to the 0 here, since that's just 1. But we don't write that. Or something like 3x to the 7th minus x plus 0.5. Things like this. These are all polynomials. Okay. These are all polynomials. There's a couple of special ones that we should talk about. And this is really just terminology is all this is. Binomials are expressions with just 2 terms. So things like x plus 7. So if you ever did word within the word or Latin roots or whatever, bi is the Latin root for 2. So we have 2 terms, x and 7 in our case. So expressions with 2 terms. That's what a binomial is. You might have heard of the Binomial Theorem or the Binomial Formula, which expresses how to take different powers of these sorts of things, like foiling many times. and get the binomial coefficients for those. Let's see, quadratics. Highest power of x is 2. So, for example, x squared minus 3x plus 7, ... Negative x squared is also a quadratic. Things like this. We also use cubic is how we say highest power is 3. We actually have words for 4 and 5. They're quartic and quintic. Those ones we don't really talk that much about. But there's like trivia for you if you're ever at a bar and they ask you what a polynomial with the highest degree power of x is 5. You'll know that it's quintic. If we ever go back to bars again. Sad face. Okay. So, man, almost out of time here. Let me erase this here. We're not going to talk about factoring. What we're going to talk about is adding polynomials. And we say, quote, combine like terms. That's the way that we add polynomials. So what do? We take, I don't know, x cubed minus 7, x squared plus x plus 3. And we're going to take that polynomial and we're going to add that to 2x cubed minus x plus 3. Okay, so what we do is we find like terms. And when I say like terms, I mean terms with the same power of x. And we're just going to combine them by counting up however many we have of each one. So let me highlight. We'll use this red color for the x term. And we'll use blue for the coefficient. So if we're going to add all these up, we should combine these like terms. So first of all, I'll do the cubes. I have x cubed and 2x cubed. Those can be combined to make 3x cubed. And I only have just this one power of x squared. And the second expression doesn't have any powers of x squared. So I'm just going to leave that alone. And then I should combine plus x with, I should add that to negative x. Well, those are going to cancel each other out. We're going to get plus 0. And then we'll have plus, well, we'll combine positive 3 and 3 to get 6. So our answer for this case will be 3x cubed minus 7x squared plus 6. Okay. So I think that's where we're going to leave it for today. If you have any questions, then feel free to stay after for a couple minutes. Otherwise, you're free to go, and I'll see you all tomorrow. I will upload the exit slip after class, so be on the lookout for that. I'll upload it in just a few minutes here. So have a good day, and yeah, if you have questions, then feel free to ask. Yep, no problem. My pleasure. Let's see here. Show the page of special polynomials making notes. Ah, I see, yes. Special polynomials. That's where you wanted to see, I think.